Hi, welcome to this mini-series of videos all about e. This mini-series is going to be focusing on e and its relationship to real exponentiation. What is real exponentiation? How is it specifically defined? In contrast with rational exponentiation, this question is not so clear-cut. Moreover, why does e appear in relationship to exponentiation in such an integral way? And what even is e to begin with? These are some of the questions that we would like to address in this series. So the motivation for this topic is, as already alluded to, it's easy to define a to the power x when x is a rational exponent, but it's not clear how this is extended to when x is a real exponent. So here a is going to be some fixed positive real number itself, and x is going to be some variable exponent. So clearly when x and y are natural numbers, we have this property here, that a to the power x plus y is equal to a to the power x times a to the power y. And in fact, it's very easy to extend that to rational exponents as well. But it's not so clear what to do in terms of extending it to real numbers, so why should this property hold? However, we do treat this property as true even when x and y are real numbers. Why do we do that? So what's the justification? So in this video, we hope to address why this property does indeed hold amongst other properties. So first of all, what are natural integer and rational exponentiation? So we claim that they're pretty easy to define, and indeed they are. A to the power n for a natural number n is simply a times a times a times itself n times over for whatever this number n is. And if we want to have negative exponents, negative integers as well, then a to the power minus n is defined to be 1 over a to the power n. It's just the reciprocal of what a to the power n was. So this accounts for all integers, positive and negative, except for 0, and we define a to the power 0 to be 1. And this accounts for all integers. And if we want to extend to some basic fractional exponents, a to the power 1 over n, where n is still a natural number here, this is defined to be the nth root of a, where the nth root of a is the unique positive number, which has the property that when you raise it to the power n, you get a. There's exactly one number that satisfies that, and so this is called the nth root of a, and this is what we define a to the power 1 over n to be. Now, using these three examples together, it's not so hard to extend from these examples of integer exponentiation and basic fractions of this form to general fractions of this form over here. So any rational number, which is a ratio of integers m over n, can be expressed in this way. A to the power m over n is defined to be the nth root of a to the power m. And so we know what a to the power m is. That would be given in one of these first two parts, depending on the sign of what m is. And n, you can assume that it's positive simply because any minus sign can get absorbed into the numerator if need be. So this was all very easy to do. This is all very natural, but what about real exponentiation? So for example, what about 5 to the power pi? Pi, as we know, is not a rational number, so it can't be written in this form. So then we can't define it to be the nth root of 5 to some power, some integer power. That doesn't make any sense because pi can't be written in this fractional way. So there needs to be a good definition for this. So we're now going to work our way up to giving a definition for real exponents. So the main questions that we want to answer in this video are the following. First, how do we define real exponentiation? And why do we focus on this number e over other numbers with regard to exponentiation? Why is it that e is so integrally tied to the definition of exponentiation in the first place? And further, what is e? How is it defined? Now, on our way to answering these questions, we're going to be running into the natural log function and the exponential function. And so first we'll need to define what is the natural logarithm and what is the exponential function. And so we'll give definitions for these functions, and amongst other things, we will see why their derivatives are defined, are given in the way that they are here. So we've been told ever since we've taken a course in calculus that the derivative of the natural log function is 1 over x, and the derivative of the exponential function is itself. Why are these properties true? We'll see why those are true amongst other properties of logarithm and the exponential function. And so these will be used en route to defining real exponentiation. So here's the outline for the path that we're going to be taking in this video. So first, we're going to start by discussing some relevant prerequisite concepts that we're going to need, and then we're going to be introducing L of x and E of x. So L is suggestively notated to represent the logarithm, the natural logarithm function, and E suggestively notated to represent the exponential function. And so we'll introduce these functions, and we will we'll deduce some relevant properties. So we start with logarithm, and we'll deduce relevant properties of it, and from the logarithm function, we're going to derive the exponential function and also deduce some relevant properties of it in turn. Then once we have L of x and E of x, we're going to define exponentiation for irrational powers via this function E of x. So we're going to use E of x as our tool for defining irrational powers, and then we're going to demonstrate the compatibility with rational exponents. So you can have a definition for irrational powers, but it's not going to be very helpful unless it's compatible with the rational exponentiation that we've already defined. So in fact, it will be the case that the irrational powers are going to be a natural extension of the rational powers. And so we'll see that, and then we'll finally conclude by illustrating that real exponentiation, which will be the combination of both the rationals and the irrationals into one general definition now, that real exponentiation, as it's been defined in this video, it exhibits the expected behavior that we want in order to be able to deduce all sorts of the algebraic properties that we're used to in terms of exponents. So this is the plan that we have for this video, so let's get started with the content now. So here's the two main prerequisite concepts that we're going to be relying on for this video. And so these are two theorems from one variable calculus. So on the left here we have the fundamental theorem of calculus, and on the right we have the inverse function theorem. So we'll address both of these in turn, first the left, then the right. So on the left here, the fundamental theorem of calculus is typically expressed in two parts, so given by these two sub-bullet points here. This first part is just saying that if we have a function f and we integrate it, a definite integral from a to b, then this is equal to capital F evaluated at b minus capital F evaluated at a, where f is any antiderivative of little f. So this is just saying that the integral of f is the difference of any antiderivative. The second part is saying that this function given here, f of x, as defined to be the integral from a to some upper bound, which is now a variable x, of this function f, this is an antiderivative of f, assuming that f is continuous, but that assumption will be met for our purposes. So in any case, the point is that the first part is saying that this integral is a difference of the antiderivative of any antiderivative, and this part is saying that this function here is an antiderivative of f. Okay, and then the inverse function theorem is giving us an efficient way of computing the derivative of the inverse function, provided that it exists. It has to meet some, f has to meet some requirements, has to be monotone, continuous, and for any given point where we want to compute the derivative, f prime of x has to be non-zero, but in any case, those assumptions will be met for our purposes. So if we know what f prime evaluated at a point x is, then we can immediately infer what the derivative of the inverse function evaluated at the image of x under f is, without actually having to go through and do any calculations, or excessive calculations, that is. We don't need to compute the inverse function, take the derivative, evaluate it at the image point here. No, all we need to do is just take 1 over the derivative of f at this original point x. So this is just an efficient way of computing this, and so these are the two theorems that we'll need in order to define the functions that we want, log and exp. So let's get on to that now. As we mentioned before, we're going to start by defining the logarithm function, and we define it by asserting this following fact here. So we assert that there exists a unique function L from the positives to the reals which satisfies the following two conditions. The first condition being that this function L, when you differentiate it, you get 1 over x, and the second property being that if you evaluate it at 1, you get 0. So conceivably, there could be many functions L which satisfy these two properties here, or maybe there's no functions at all which satisfy these properties. But in fact, the claim is that exactly one function will satisfy these two properties, and therefore that defines the function in terms of these two properties. So since it defines the function, we can denote this function by log of x. So before we move on, let's actually prove that this claim is true and see how we can define logarithm in terms of these two properties. All right, so here we are at the whiteboard, and we're going to prove this statement on the slide that we copied over here. So the statement is saying that there's a unique function L which satisfies these two properties. The first property being that, that L prime of x equals 1 over x, and the second property being that L evaluated at 1 equals 0. So again, there could be many functions which satisfy those two properties. There could be 0 functions which satisfy those two properties. But in fact, it's exactly one function which satisfies them. And so we're going to prove that now. So first of all, we're going to suppose that L exists. This is to say that at least one function L satisfies these two properties. Later on, we're going to demonstrate the existence of it. But for now, we start with existence, and from existence, we show uniqueness. So, so right now we want to show that there's exactly one function, assuming that a function exists at all. All right, so since L exists, this means that, so we'll just say this implies that L is an antiderivative of 1 over x. And that's because this is by property 1 above, so we'll just put a 1 underneath this implication arrow here. So L prime of x equaling 1 over x is the same thing as saying that L is an antiderivative of 1 over x. Okay, and so since it's an antiderivative of 1 over x, what that means is that if we take the integral of 1 over x, but instead let's call it 1 over t, using t as a dummy variable here. So we integrate 1 over t dt, and we'll integrate from 1 up to x. Now, what this means then, so this means that we can express this by the fundamental theorem of calculus. We can express this as a difference of antiderivatives of 1 over t. So what is this difference here? It's antiderivative we're going to choose is L. And so it's L evaluated at the upper bound, which is x, minus L evaluated at the lower bound, which is 1. And then finally, using the fact that L of 1 equals 0, this just simplifies to L of x. So in other words, this part vanishes. It equals 0 to claim 2 above, or sorry, property 2 above. So in other words, what we've just done is we've just shown that L of x, if it exists at all, is defined in this way. It's the integral from 1 to x of 1 over t dt. Now, this doesn't necessarily mean that this function does satisfy the properties. It just means that if a function satisfies the two properties, it must be this function here. So this shows L is unique if it's existing at all. So we do have uniqueness. Now we'll show the existence because we'll show that this function does indeed work. So what we want to show is the two properties above. So first of all, if we differentiate this function, what happens when we differentiate this function here, the integral from 1 to x of 1 over t dt? Well, again, by the fundamental theorem of calculus, this is going to work out simply to be 1 over x. And this shows, indeed, that L prime of x equals 1 over x. So we can say, therefore, L prime of x equals 1 over x. So that's property 1 being satisfied. And then second of all, is it true that when we evaluate at 1, we get 0? So let's plug in x equals 1 here. And obviously, this is going to be 0 because the lower and upper bound of the integral are the same. So we can say, therefore, L of 1 equals 0. And so property 2 has been satisfied as well. So this function here, the function given by L of x, defined to be integral from 1 to x of 1 over t dt, is the unique function which satisfies these two properties. And so that proves this claim from this slide here. Okay, so now we can go back to the slides to keep going. We just finished proving that there exists a unique function L which satisfies these two properties given here. And so since this function is unique, we can think of these two properties as defining this function L. And so we give this function some notation. We denote it by log of x. And it's important to distinguish this log of x function from the log function that we're all familiar with from algebra and calculus courses. Of course, they're inevitably going to end up being seen to be the same thing, but the difference here is that we can only assume that log of x, as it's been defined here, it only has the properties that we've shown it to have so far. So there's all sorts of properties of logarithms that we cannot assume that log has as of yet. Just because we're using the familiar notation doesn't mean we can use those properties. We would want to prove those properties are true based off the definition we've given here. So here is a list of some of those properties that we're all familiar with the log function, and indeed the log function that we've defined here does have these properties, as it must, of course, if it really is the genuine logarithm function. So here, a and b are going to be positive real numbers, and r is going to be a rational number. And a, b, and r, as you can see, are the parameters that show up in these algebraic properties here. There's also some analytic properties down here. For instance, 5 and 6 are talking about the asymptotic behavior of this function. But for example, number 1 is maybe the most popular property, the fact that multiplication inside the input can be broken up as addition, and there's some similar properties here, but in general these first three properties we can view them as algebraic properties, and the latter three properties can be viewed as analytic properties. Let's not get too carried away with proving all these things, but let's at least prove some of them in order to get a feel for how we can prove properties of logarithm based off the definition we've given. In particular, let's prove property 1 and part of 3, and we can also show that 4, 5, and 6 follow very quickly as well. So those will be the properties that we show. So let's go back to the whiteboard and prove these things now. Okay, so we're back here at the whiteboard, and now we're going to prove some of these properties appearing on this list on the slide that we copied over. So in particular, the items that we're going to prove are 1, part of 3, so we'll indicate that with an asterisk, and then 4 through 6 are all simple, so we can prove those without much trouble. So the details of the others are very similar, namely 2 and the rest of 3. They're very similar to what's already going to be done. And let's keep in mind what logarithm is in the first place so that we can prove these properties of this logarithm function. So we know that we can justifiably define it to be the function, the integral from 1 to x of 1 over t dt, but really the reason that that was even justified in the first place was based off of two properties which demonstrated the existence and uniqueness of this logarithm function. Namely, first of all, that the derivative of logarithm is 1 over x, and second of all, that log evaluated at 1 is 0. So these two properties are really the defining properties that we're going to be using in order to prove the items from this list that we now want to prove. So let's see how that goes. So we're just going to prove these items one by one, starting with part 1 above here. All right, so we're going to start with item 1 here. So let's just scroll down, and item 1 is saying the following. It's saying that log of a times b is equal to log of a plus log of b. And so what we're going to do is, since we have two arguments, two parameters here, a and b, we're going to think of one as fixed and one as a variable. So we're going to think of a as fixed, and think of b as a variable. And so the significance of this, and also, by the way, we're just going to replace b with x, just because that's more suggestive of variable notation. The significance of this, then, is that what we can do is, now it's equivalent to prove. The above that we want to prove is equivalent with log of ax minus log of a is equal to log of x. So what we want to do is we want to show this. We want to show that this is true. So how do we show that a function is equal to log of x? Well, what we do is we use the defining properties that we see above here, a and b. So we're going to demonstrate that this left-hand side really does have those properties, and therefore it must be equal to log of x, which is the right-hand side. So here's how we do that. So first, we're going to differentiate the left-hand side. So d by dx of this left-hand side here. And so what that comes out to be is we're just going to distribute the differentiation operation inside. So it's the derivative of log of a times x minus the derivative of log of a. And that is going to be equal to, well, using the fact that for this first part, the derivative of logarithm is 1 over the inside, which is ax. And then by the chain rule, we multiply by a. And then minus 0, because the derivative of any constant is going to be 0. And so we see that, of course, the a is going to cancel with that a, and what we're just left with is 1 over x. And so indeed, we see that property a has been satisfied. When you differentiate this left-hand side, you get 1 over x. So now let's find out what happens when you plug in 1, because that's the other property. What we want to have happen is we want this to equal 0. So now, I'll just put a line here to separate. So log of a times 1, minus log of a, this obviously is equal to 0. And so what that means is that property b has been satisfied. When you plug in 1, you get 0. There's a unique function which satisfies both of these properties, and this left-hand side has satisfied both these properties. Therefore, this left-hand side must be the logarithm function, and that is what this expresses right here. So we've just shown this by showing that the left-hand side satisfies the defining properties of logarithm. So therefore, we've just shown this, and so then just rearranging, if we put the log of a back on the other side, and we replace x with b again, just so that we could get back to the initial notation, we do indeed find that, that this property above is true, that log of ab equals log of a plus log of b. Next up, we want to prove property 3 from this list here, or at least the modified version of 3 that we're going to prove. So this is property 3 on the slide. If you can see, it says that we can basically pull exponents down in front as coefficients. This is specifically for rational exponents, as real exponents, of course, have no meaning yet. That's what we're trying to work towards. But for rational exponents, we can perform this operation. And so we're going to show for some rational exponents that we can do this. We're not going to do all rational exponents. But let's go down here and make some more space, and we can prove now 3 asterisk, I guess. And so what 3, without the asterisk, is saying is that that log of a to the power r is equal to r log of a. And so here r is a rational exponent. And of course a is still any positive real number. Okay, and so the way we're going to prove this is, well, we're only going to prove it for certain cases. First of all, let's take a look at a few obvious cases. R equals 0 and 1. In the case of r equals 1, this is trivial. And in the case r equals 0, you can just see that a to the power 0 is 1, and we know that log of 1 is equal to 0. and 0 would also be the right-hand side in that case. So 0 follows immediately as well. So for those two cases, it's immediately true. So now let's try the case r equals 2. So what would happen in the case r equals 2? We would have log of a squared. And so what we want this to be equal to is 2 log of a. What it's actually equal to is log of a times a. But now we can use this property 1 that we've already shown, which is that we can break up the multiplication as addition. So this becomes log of a plus log of a, and that is, of course, 2 log of a. And so that shows that for r equals 2, this is also true. And now, more generally, if we take r equals n, where n is some natural number, we can show that log of a to the power n is equal to n log of a. I'm writing this on the right-hand side. Basically, you just the proof is by induction, and what you do is when you want to prove the case log of a to the power n plus 1, this equals log of a to the power n times a. And then you break it up just as we did and use the induction hypothesis, and this will end up equaling n plus 1 log of a. And that, of course, satisfies the induction proof that you need. So anyways, so what this shows is that for any natural number, this works too. So that's just a sketch, but the proof is exactly the lines that we just wrote in the case of a squared. Now you're just replacing the first a with a to the power n instead. All right, so that takes care of any natural number. Now, what about the case r equals minus 1? So this will at least get us started in the negatives. And so in this case, what we have is log of a to the power minus 1. And what we want, so we want this to be equal to minus log of a. So this is equivalent with showing that if we just add that to the left-hand side, we have log of a to the power minus 1 plus, let me rewrite that plus there, so plus log of a equals 0. And so this is equivalent with turn the addition now into multiplication on the left-hand side. We get log of a minus 1 times a, and this equaling 0. And of course, this is equivalent with, we just simplify, this is log of 1 equals 0, because a minus 1 times a equals 1. And this bottom statement is true. And so what we've just shown is that this top statement here is equivalent with this bottom statement, and the bottom statement is true, so the top statement is true as well. You can just do this algebraic rearrangement that we just showed. And so for the negative 1 exponent, this property is also true. Now, the last case we'll address is the case of some basic fractional exponents. So r equals 1 over n, where, again, n is going to be some natural number. So now we're just considering, 1/2, 1/3, 1/4, etc. And so, again, we're going to have something that we want here. So log of a to the power 1 over n, we want this to be equal to 1 over n times log of a. And so, again, we're just going to do some algebraic rearrangement and arrive at a statement which we already know to be true, thereby justifying this statement here. So what we do is we just multiply by n on both sides. So we get n log of a to the power 1 over n is equal to log of a. And now we use the fact that we've already shown that for natural number exponents, we can turn coefficients into exponents. So this is if and only if. What we do is log of a to the power 1 over n, that quantity now to the power n. So we took this n here, and we turned that coefficient into an exponent. So this, we just keep the right-hand side as is. And of course, now we just simplify. So equivalently, simplifying, we get, a to the power 1 over n to the power n is, of course, just a. So we have log of a equals log of a. And obviously, this is a true statement, of course. And so therefore, that justifies that this initial statement here is true as well. So for basic fractional exponents, we have that the coefficients and exponents can be interchanged. So this will conclude as much as we're going to do for part 3. You can continue for all the fractions, positives and negatives, if you want, but just take some more time. But this gives you the idea of how this proof works. Now finally, we want to show these analytic properties from above. So going back to the top here one last time, what we see on these slides, on the single slide here for these final 3 properties, first of all, it's saying that the function log is strictly increasing over its domain. Property 5 is saying that asymptotically, as we let x grow arbitrarily large, the function grows arbitrarily large. And as we let x approach its left-hand limit, which is 0, so we're approaching that from the right, of course, because log is only defined on positives. That limit, the function log is approaching minus infinity. So it's unbounded, going off to positive and minus infinity as it approaches the endpoints of its interval in each direction. So, and it's increasing all the while it's doing those things. So if you think about it, these 3 things together would really justify the picture of log that we have in our minds, which is something like that. So that overlap with the slide is a bit distracting, but hopefully you see the function here. This graph of log of x would be justified, or at least some rough approximation of this is justified based off these properties 4 through 6 here. So you see that it's increasing and it's unbounded to the right, going off to positive infinity, and unbounded to minus infinity as it approaches the y-axis. Okay, so let's prove these things down here at the bottom. So here we go. So proof of 4 to 6. So what we basically want to show is that this graph here is justified. That's the picture that encapsulates those 3 properties together. So first of all, for 4 said log is increasing. So we'll just kind of be brief about writing that. So log increasing. Why is that true? Well, it's simple, because if you differentiate this function, differentiating log of x, it gives you 1 over x, and that's positive because x is positive. And so if the function's derivative is positive, that implies that the function itself, which is log of x, is increasing. So that's just immediate based off the fact that its derivative is positive. Okay, now for number 5 here, 5 is saying that this behavior to the right here. So as we let x grow arbitrarily large, the function is supposed to go off itself and grow arbitrarily high. So x approaching infinity implies that log of x is also approaching infinity. Okay, so what we would do is, for example, let's just consider the sequence x sub n equals 2 to the power n. So just the powers of 2. And so obviously, this sequence, so x sub n is going to infinity as n goes to infinity. That's, of course, clear. So we're thinking of these x sub n's as inputs here. So now what's happening, so log of x sub n, this is log of 2 to the power n, and this becomes n log of 2, because we can pull the natural number exponent down in front is a coefficient. So this was by property 3 from before. And now let's just take note of the fact that log of 2, this is strictly greater than log of 1, because we're using the fact that this is by 4, the fact that the log function is strictly increasing. We probably should have put that above. It's log is strictly increasing because the derivative is strictly positive. And so anyways, we have log of 2 is strictly greater than log of 1 then because of that. And log of 1 is of course 0. And so what this shows is that log of 2 is strictly positive. So n times some strictly positive number, as we let n grow to infinity, that means that that implies that this quantity here, which is n times log of 2, or in other words, log of x of n, this is also approaching infinity. And so that basically shows what we want then. We've just found a sequence of successively growing input values, which are the powers of 2, and as you grow those input values, the function itself is tending off towards infinity. So that shows why the function is unbounded to the right. All right, and finally, for property 6, the last one that we want to show is we just want to show that the opposite limit also holds. So limit as x goes to the 0 from the right of this function log of x, we want to show that this equals minus infinity. And so what we can do is, just looking back at this picture one more time of this graph is supposed to be accurate, and what this graph is showing here is that on this left part now, you can see that as this graph is approaching the y-axis, or in other words, as x is approaching 0 from the right, the function is becoming arbitrarily negative. So as we're tracing down this direction, down to the left here, it's going all the way down to minus infinity. All right, and so the way that we show that, so let's just put a little separation here. So finally, so the proof of this is first, let's just rewrite the left-hand side as a limit as y goes to infinity of log of 1 over y. And so this is equal to this left-hand side from right here, from the above. Why is that? Well, it's just because, as y goes to infinity, 1 over y is going to 0 from the right, by the way, because 1 over y is always positive, and as long as y is positive. And so, and finally, we're just using the fact that log is continuous because it's differentiable. So that makes it continuous, and so this is just an equivalent way to rewrite this limit here. And so let's evaluate what this comes out to be then. And so this is equal to limit as y goes to infinity of log of y to the power minus 1 is a more suggestive way to write that, because now what we can do is, of course, we know that we can pull exponents down in front as coefficients. And so this becomes limit as y goes to infinity of a minus log of y. And this minus sign, in fact, can be pulled out one more time. So this equals, we can pull it out in front of the limit itself. The limit as y goes to infinity of log of y. So as y goes to infinity of log of y, this by property 5, we just showed that this is infinity, but let's include the minus sign in front, so we have minus infinity in total. And so that shows that we get the right-hand side, which is what we wanted. We've now shown that logarithm really is the familiar function that we've been accustomed to in our previous exposure from algebra and calculus courses. That is, logarithm really does have these familiar properties that we use all the time. But the difference now is that we've proven them based off the definition that we initially gave for logarithm. And so now with this logarithm function in mind, we can do a similar thing with the exponential function. And so we are going to assert in an entirely analogous way there exists a unique function e from the reals to the positives such that it satisfies these two properties. The first property being that the derivative of this function is itself, and the second property is that when you evaluate it at 0, you get 1. And so this will be a unique function, and as such, we're going to give it some notation. We'll call it exp of x. So now, quite similar to what we did before, we're going to go to the whiteboard and prove that this function exists, and it's unique. However, one difference will be that instead of starting from scratch, we're going to use the logarithm function and define this function as the inverse and see where we can go from there using the inverse function theorem. So let's go to the whiteboard and see what we can do in terms of proving this statement here. All right, so we're back at the whiteboard, and now we want to show the theorem on this slide, that there exists a unique function e from the reals to the positives, satisfying these two properties here. So we're going to denote these two properties by e1 and e2, respectively. So e1 being the property that the derivative of the function is itself, and e2 being the property that when you evaluate this function at 0, you get 1. And just as in the case when we were proving the unique existence of the log function, what we're going to do in this proof is we're going to start by assuming that the function that some function satisfies those properties, and then we're going to prove uniqueness first. So we're going to show that if a function satisfies these properties, there can only be one such function. So first of all, we'll consider any function e satisfying the properties e1 and e2 above. And the first thing we're going to do is we're going to prove a claim about such a function e. So the claim will be that such a function e has an additional property we can derive, namely that it's non-zero. So e of x is non-zero for all x in R. And so the way that we're going to prove this is, it's a little tricky, but once you see how it goes, it's pretty interesting, really. So we'll consider a new function. So consider the function g of x, which will be defined to be the product e of x times e of minus x. And we're going to see what results we can deduce about g of x. When we take the derivative of g of x, so we'll just put some square brackets there, what we get is we're going to have to use the product rule. So why are we differentiating in the first place? Well, it'll become clear later once we end up justifying this claim. So this is just a necessary step to take in order to prove the claim that we want. So we're going to use the product rule here, and so this becomes the derivative of the first term, which is e of x, and that times the second function in the product, e of minus x, and then plus the first function, e of x, times the derivative of the second function, e of minus x. So now, simplifying this, we use what we know about the function e now. So by property 1, or more specifically e1, this simplifies to the derivative of e of x is itself, and then times e of minus x. And then for the right-hand term, what we have is that the derivative of e is still itself, but now we have to include a minus sign due to the chain rule, since we have a minus inside the argument. So the plus becomes a minus, and then this is so still e of x times now e of minus x. And if you take a look at what we have here, this actually is just 0. It's the same thing. This term is equal to this term. And so what that means then is we just differentiated this function g and we got 0. So that implies that that this function g of x is constant. So it's we use this triple equal sign just to note that it's constantly equal to the same number, independent of the input x. So it's just a constant value. We don't know what that value is, but it's just some fixed number that g is constantly equal to. But in fact, we can figure out what that number is. We can plug in 0 because we know something about what happens when you plug in 0 to the function e. So here we get e of 0 times e of minus 0, which is again 0. And we know by property E2 now that this is 1 times 1, which is 1. So this 1 must be the constant number that g is equal to. So g of x is equal to 1 constantly. So finally, what this means is that it's never 0. So g of x being non-zero, what this means, so we'll write this down below. So g of x is never 0 for all x and r, and that in turn implies that the function e of x is never 0 for all x and r. Because if there was some point, some x value for which e of x was 0, then of course, just use that x value and plug it into g, and you'd have 0 times something else, and so g would be 0. But of course, that never happens. It's constantly equal to 1. So what we have here is this is the result that we wanted to prove. This was the initial claim that e of x is never 0. Now that we've shown this claim, we can use it to prove the uniqueness of this function e. So what we're going to do is we're going to consider two functions. So consider e and f satisfying the above properties, e1 and e2. And what we can say then is we're going to have the following claim, which will prove uniqueness. The claim is that e equals f, as functions, by the way. So whenever you have two things that both satisfy these properties and they are forced to be equal, then that means that there can only be one thing that satisfies these properties, at most one thing. So the way that we're going to prove this claim now, so this is the claim of uniqueness. So we'll say here, i.e. uniqueness. The proof is we're now going to consider the following function. So consider the function h of x, which is defined to be the ratio of these functions, e of x over f of x. And let's keep in mind that h will map us from the reals to the positives. And it's well defined for all x. So we'll say for all x in R because the denominator is never 0, as we've already shown. So because f of x is non-zero for all x in R by claim number 1. So that's why we showed that first claim, so that we could consider this ratio of e over f and have that be a well-defined function. So now that we can do that, let's see what we can deduce from this function h. So just as before, we're going to differentiate this function. So the derivative of h of x, this works out to be using the quotient rule now. So it'll be the bottom function times the derivative of the top, which we can just abbreviate as e prime of x, and then minus the top function times the derivative of the bottom function, and all over the bottom function squared. So that's what we get by the quotient rule. And we can simplify this, of course. This just becomes f of x times e of x, because e prime of x is equal to e of x, and then e of x times f of x. And as you can see, this will be over f of x squared. So this was using property e1 again. And so this simplifies now just to 0, because again, you can see that the numerator here is the same thing written twice. It's the same thing minus itself. So this simplifies to 0. And so again, what we can conclude is that now this function, h of x, is constantly equal to some constant number. And again, we don't know which number, but we can figure it out. And so let's plug in 0 and see what we get. Well, it's e of 0 over f of 0. And by property e2, this is just 1 over 1, which is 1. So again, this constant must be 1, and so now what we have is that this ratio, h of x is the ratio e of x over f of x, and that ratio is constantly equal to 1. So in other words, this is the same thing as saying that e of x is constantly equal to f of x. That's for all x. Or in other words, that the function e is equal to the function f. And that is what we wanted to prove for uniqueness. Now that we've shown that there's a unique function satisfying these properties, if a function is going to exist at all, let's show that such a function actually exists. So this is the existence portion. And so the function that we'll be considering is taking e to be the inverse log function. Now, why should this work? The first question to even consider is this well-defined? So is log inverse well-defined? Is log invertible in the first place? And the answer is yes, and this is because log is strictly increasing. This is one of the properties that we exhibited before. So strictly increasing, and so due to the fact that it's strictly increasing, that means that it's 1-to-1, and so if it's 1-to-1, it's invertible on its range. So this is a well-defined function then. The question is, what is its domain and range? So the log function's domain and range, well, log, we said, mapped us from the positives to the reals. Now, the question is, the reals here, this is the codomain, but it's not clear whether it's actually the range or not. The range is the numbers that log actually achieves. That we're just saying that it's contained within the real numbers right now, but we don't know if we hit all the real numbers. But in fact, we do. And this is because we have the asymptotic behavior of the log function. We know that the limit as x goes to 0 from the right of the log function, this equals minus infinity. And similarly, as x goes to plus infinity, the function log itself goes to plus infinity. And so because of that, and finally we know that log is a differentiable function, so that means it's continuous. So we have a continuous function which asymptotically goes to minus infinity and plus infinity, so it has to hit every value in between. So r is in fact not only the codomain, it's actually the range. Every number in the reals is achieved by log. And so it makes sense then to consider the inverse log function. So actually, let's just reverse this arrow over here. So the inverse log function takes us from the reals to the positives. So we'll write that over here. So e, the inverse log function, is going to send us from the reals to the positives, which is exactly as we wanted, as specified by the slide above. So now let's think about the properties E1 and E2 that need to be satisfied. So just as a reminder, so E1 being the property that E prime of x equals E of x, and E2 being the property that E of 0 equals 1. Okay, and let's just separate this a little bit so that we don't mix things up. All right, now first of all, this property E2, this is trivial. Why? Because we just established that we're taking the inverse log function, and we know that log, it sends the number 1 to the number 0. So in other words, when you input 1 into log, you get 0. So then going the other direction, this is now e, which is sending us the opposite way. It's sending us from 0 to 1. So in other words, e of 0 equals 1. So we trivially satisfy property E2. The only thing we really need to check is the derivative of this function actually equal to itself? So how are we going to reason about that? Well, let's think about what the derivative of the log function is, and we're going to use now the inverse function theorem as mentioned before. So here's how we're going to do that. So e prime of x, So this is, we can just rewrite it. It's log inverse of x. So differentiated. So we're taking prime of that. And now we can rewrite this one more time. Log inverse prime of, we're going to say log of y. And why are we doing that? Well, you'll see why in a moment, but we can do this because the inputs for the exponential function, in other words, the inverse log function, are the outputs of the log function. So here we're saying that x equals log of y, and that's the same thing as saying that y equals e of x. So just as a picture here, we have that x is being sent to y by e. That must mean that y was being sent to x by log, because these are inverses of each other. So in other words, we have this, that x equals log of y, and y equals e of x. All right, and now what we can do is we can use the previously mentioned inverse function theorem. So we'll write IFT here. And so this gives us an efficient way of computing the derivative of the inverse function. And it's given as follows. It's 1 over log prime of y. So we just evaluate the original function log, the derivative of it, at the input for that function, which was y. Now, the question is, can we do this? Is the step that we just made, is it justified? Can we use the inverse function theorem? And we can, because what we need is for the function log to be monotonically increasing, strictly increasing, and we do have that. We've already established that log is a strictly increasing function, and it's differentiable. Therefore, its inverse is also differentiable and given by the inverse function theorem. So this step is justified because we've met the necessary hypotheses of the inverse function theorem. So now we know what the derivative of log is, so we can do some more simplifications. This is 1 over, the derivative of log is 1 over y. So what we have then is 1 over y, or in other words, y, but y is nothing more than e of x, as we've just mentioned. So in total then, combining all these chains of equalities here, we have that e prime of x is equal to e of x, and this establishes property E1, which we wanted to show. So, that shows that this inverse log function really does satisfy the above properties, and it's the only function that does. So this concludes the proof of the existence and uniqueness of this function that satisfies these properties, and we're going to be calling this function, the inverse log function, we're going to be calling it the exponential function, as you're already anticipating, and we're denoting it by exp here. So exp is mapping the reals to the positives. So now we can go back to the slides and continue discussing the properties of the exponential function. Now that we've seen that these properties uniquely define a function, in particular the inverse log function, otherwise known as the exponential function, we can, in an entirely analogous way to what we did with the logarithm function, we can deduce some relevant properties about the exponential function. So let's go on to some of these properties. And so again, these will be the properties that we would expect the intuitive exponential function to have. So this really does line up with what we would have already anticipated. So here's some properties, and again, a, b are going to be real numbers as parameters in here. R is a rational number, and you can see that we have some properties here. They're quite similar looking in nature to the properties that we had for the logarithm function, which would make sense since we're talking about the inverse log function after all. And so again, we can break these up as algebraic and analytic properties. So for example, up here, this first property is the exponential function is strictly positive, and that's actually something that we've already shown due to our work towards demonstrating the uniqueness of the exponential function. And then the rest of these properties are entirely symmetric with properties from the logarithm function. So instead of proving these properties using the definition of the exponential function, we can use the logarithm function and its properties and build those into the inverse log function, or otherwise the exponential, and see that these properties follow very quickly from those. So just for example, let's take a look at property 2 here. So for 2, if we consider x of a plus b, well, we know that the inputs for the exponential function are the outputs of the log function. So a, we'll consider that as a log of x for some x, and b is a log of y for some y. So here x and y would be positive numbers. And anyways, so what we can do is we can rewrite this then as x of log of x plus log of y. And the advantage now is that we already know properties of logarithm. And so in particular, we can turn addition into multiplication. And so this is x of log of x times y. And now we can use the fact that the exp and log are inverse functions of each other. And so they undo each other, and we're just left with xy. Or in other words, this is exp of a times exp of b, since up here again, we can just apply exp on both sides and we would have that result. So then we get, through this chain of equalities here, we get that exp of a plus b equals exp of a times exp of b. So that's following immediately from the fact that we have already deduced an analogous property for logarithm. Let's just try one more. Let's try this property here. If we have exp of Ra, where r is a rational number, keep in mind, we only know how this works for rational exponentiation in terms of this exponent here. But in any case, we're still thinking of a as log of x. Then we can write this as exp of r times log x. And now we just use the logarithm properties that we already know. In particular, what we can do is for rational exponents, we can take the coefficients and turn them into exponents of the input, just like that. So we have log of x to the r. And again, exp and log undo each other, and so we're just left with x to the power r, and x can otherwise be written as exp of a. So we have exp of a to the power r. And so that shows this fourth property is true. And in a similar way, we can show all these properties are true, including the analytic ones, just using the fact that the exponential function is the inverse log function. In particular, for these analytic function properties here, these properties, it's strictly increasing. That follows from the fact that log was also strictly increasing, and this asymptotic behavior also follows from the asymptotic behavior of log, and it would suggest the picture that we're quite familiar with. So this graph of the exponential function is lining up with these analytic properties here. So everything is consistent with what we would expect. Okay, great. Now, the one consequence of property 4 on the previous slide, the one that says that the exponential of r times a is equal to the exponential of a to the power r for rational values of r, if we, in particular, take a equals 1, then what this equation simplifies down to is right here, we would have exponential of r is equal to the exponential of 1 to the power r. That's the simplification. And so a way of interpreting this is that exp of 1 generates all values exp of r for rational r. So in other words, if we wanted to know what exp of r is when r was a rational input, in principle, what we could do is we could just start with the value exp of 1, which suppose we already know, and then we would raise that value to the power r for this rational exponent, and that quantity would give us the value of exp of r. And so in this sense, all we really need to know is what exp of 1 is, and then just raise it to rational powers to find out what the value of that rational input for the exponential function would be. Now, we can't do this for real exponents, or for real inputs, we should say, because we would have to do real exponentiation. Of course, we still don't know what that is. But for rationals, we can do this, and this is going to inspire how we end up defining real exponentiation in the first place. So this is a useful insight to have, that exp of 1 generates the exponential function for the rational inputs. Now we're finally ready to give our definition of real exponentiation as an extension of rational exponentiation. So first, let's note that if we were to compute this quantity here, exp of r times log of a, where r is, again, a rational number, well, we know from property 4 of the exponential function that we just discussed on the previous slide that we can take this number r here appearing in this argument, and we can extract it outside as an exponent. So we have this quantity here then. It's exp of log of a to the power r. So it didn't really matter what this number here was. It could have been anything. It just so happens that it's log of a. But since it is log of a, then exp and log undo each other, and so we're just left with a and then to that power r still. So therefore, if we just read this backwards now, what we have is a to the power r is equal to exp of r times log of a. All right, now let's take note of something special here. The left-hand side is defined only for rational numbers r, but the right-hand side is defined for any real number r. As you can see here, it only makes sense to consider rational exponents here on the left-hand side, but on the right-hand side, the exponential function could, of course, accept any real number input. So this didn't, if we're just looking at this right-hand side expression, independent of its relationship to the left-hand side, it's perfectly fine. It would make sense if r was any real number. Therefore, this observation is going to inspire our definition. It's going to inform it. So for real exponents, we define real exponentiation. A to the power x is defined to be exp of that number x times log of a. So we're doing this based off of this observation that we just made here about rational exponents. So now we're extending the property to real exponents via definition. So the way we can read this is that if we're calling a the base and x the exponent, what we have is the base to the power of the exponent. It's equal to exp of the exponent times log of the base. So that's the quantity appearing on the right-hand side, which is the definition of real exponentiation. So this is consistent with rational exponentiation. So if we were to simply take this number x to be rational, it would make sense in terms of what we already know about rational exponentiation, because that's why we defined it to be the way it is. It's based off of this observation that we already made about rational exponents up here. So this is a natural extension then, and so this is a good way to make sense of any real exponent. Okay, now let's just make one more observation here. Let's note that if we were to consider exp of 1 and raise that to the power x, so this is going to get a little confusing just for a moment. The notation is about to get convoluted. So exp of 1 will be the base, and x will be the real number exponent now. So what we just said is that this is, by definition, it's equal to exp of x times log of the base, and the base was exp of 1. So we see exp of x times log of the base being exp of 1. So here log and exp will undo each other, and we're just left with this 1. And so we have exp of x times 1, or in other words, exp of x. And so what that means is what we see is that exp of 1 generates all exp of x, which is something that we had already said for rational exponents. But now this is for all real exponents. So again, all we really need to know in principle is what exp of 1 is. And then if you want to know what exp of x is, all you do is you just raise this number, exp of 1, to that power, and that will give you the quantity exp of x. So, so everything is based off of this single number exp of 1, and in this sense it generates it. So again, when we say raise it to the exponent of some number x, it's given by this definition now here. So we're taking exp of that exponent times log of the base. So that's what it means to do real exponentiation. Given the importance of this number exp of 1, we're going to give it some special notation. So we introduce the notation e, and it's defined to be exp of 1. So this is where our favorite number e comes from initially. So it's by definition this quantity here. And later on in future videos, we're going to be able to quantify this number and see that it really is the familiar number that we're all used to. But for now, let's keep working with our new definition of real exponentiation and see a sampling of some of the properties that real exponentiation satisfies. Now that we have a definition for real exponentiation, we can see why some of the familiar properties that we're used to about real exponentiation are indeed true. So here's just a sampling of a few of the properties that we use all the time about real exponents. For example, a to the power x and then that to the power y, that's equal to a to the power x times y. A to the power x plus y is a to the x times a to the y. The derivative of a to the power x, where here the variable is the exponent, is again a to the power x, but now times log of a, where log is the function that we've defined previously, and the derivative of x to the p, where now the variable is the base, but we still have a real exponent. The derivative of this is p times x to the p minus 1. So let's not prove all of these, but let's prove just these middle two. And in the case of all four of these, it just follows immediately from the definition of what real exponentiation means. So starting with the second item here, a to the power x plus y, this is nothing more or less than exp of the exponent, x plus y, times log of the base. That's what it means to have a to the power x plus y. And so now, if we just do some basic manipulations, we have exp of x log a plus y log a. That's all inside the argument of exp. And now we use the property of exp, which is that we can break the addition up into a multiplication. So we have exp of x log a times exp of y log a. And of course, this is by definition a to the power x times a to the power y. So we have a to the x plus y is a to the x times a to the y. So that would show that second item. Again, this is just immediately coming from the definition. We can also just work on the third item. So when we take the derivative of a to the power x, well, by definition, that means we're taking the derivative of exp of x log a. That's what a to the x means. And so when we take the derivative of the exponential function, we've already established that we just get the exponential function back again. So it's again exp of x log a, but now we have to multiply by log of a due to the chain rule, because we see a log a inside the argument of the exponential function there. And of course, again, we just have exp of x log a, that's a to the x. So we have a to the x times log of a, and that's the quantity that we see here on the right-hand side. And so, so this would demonstrate this equality of this third item here. So this is just an example of how to use the definition to prove some familiar properties of real exponentiation. So now we've given a definition of real exponentiation, and we've seen that it has the properties that we would expect it to have. One final point to discuss is with respect to alternative bases for logarithms specifically. We've implicitly already discussed alternative bases for exponentiation. For a base a raised to a power x, we've now defined that to be the exponential function evaluated at x log a, for a being any positive base. So this accounts for any number a, but we want to do the same thing for logarithms now. So no doubt you've seen log base a of x as notation before. What does this actually mean? How can we define this in terms of what we've already done? So what we want is for log base a of x to be a number y such that a to the power y equals x. So this is truly capturing the spirit of the logarithm function being the inverse of the exponential function, now just with respect to a different base a. Basically, we have this equation, a to the power y equals x, and we just want to solve for y. So if we have a to the y equals x, then we know what a to the power y is. This is, by definition, x of y log a. And we just want to solve for y now. So what we can do is we can just take the logarithm of both sides to undo the exponentiation. And so what we'll have is y log a equals log x. And then finally, we can just divide by log a. So y equals log x over log a. So this value here is the only number that could possibly be the solution for that equation as we've derived, and indeed it is. So then what we do is we define log base a of x to be that number, log of x over log of a, where the log function without a subscript, that's just the function that we've already defined. So we're defining something new in terms of what we already know. Okay, so a few things to note. First of all, log base e of x, that's equal to log of x, just as functions. You might also sometimes see this notated as ln of x, that's the natural logarithm of x, but here we're just calling it log of x. Now the reason that that's true is if you just use this definition and see what log base e of x is, what you have is log base e of x, that works out to be log of x over log of e, and log of e, that's log of x of 1, using our definition of e. And of course, log of x of 1, those functions undo each other, and you're just left with 1. So, so you have log of x divided by 1, basically, and that just leaves you with log of x. So, so that shows you that log base e of x really is just log of x. So if at any point we omit a subscript from the logarithm function, then it's understood that what it really means is it's the logarithm with respect to base e. And we can also make it explicit by putting that subscript of e there. Now, one other point to note is that log base a of x, not only is it log of x over log of a, it's also log base b of x over log base b of a for any positive base b. So again, you can just do some algebra to work that out. What you have is log base b of x, using our definition now, is log of x over log of b, and then you're dividing that by log of a over log of b. And then you notice that these log of b's will cancel each other out, and you're just left with log of x over log of a, or in other words, log base a of x. So that shows that these two things are equivalent to each other. And so really, log base a of x, we defined it in terms of the initial log function, log of x over log of a, but it doesn't matter which base you take it with respect to, as we've just shown here. You could also do log base any other number and do this division, and the same quantity would pop out at the end. So this illustrates how to change bases, going from a base a to a base b, if you want. Now, in principle, we can use any base b that we want, but in practice, the most common bases that you'll see are the ones listed here. So log base e of x, for obvious reasons, that's what we've been working with. Also log base 10 and log base 2. Log base 10 because we work in the decimal system for representing numbers, which is inherently base 10, and log base 2 because we oftentimes work with computers that represent things in binary. When doing computations, you might see log base 10 or log base 2. When doing abstract math, you might see log base e more often. But in any case, this addresses exponentiation and logarithms with respect to any base. Now let's go on to summarize what we've done in this video up to this point. At the beginning of this video, we gave a list of questions that we wanted to have answered by the end of the video. Well, here we are at the end, and we are able to answer each of these questions now. So just to remind us of what this list was, first, how do we define real exponentiation? Then why do we focus on e over other numbers regarding exponentiation? And then what is the log function, and what is e to the x? And why do they have the derivatives they do, amongst other things? Now that we've gone through all the information in this video, we can give explicit answers to each of these questions. So let's answer them in the order that we addressed them in this video. So first, starting with the log function, we said, so what is it? We said that there was a unique function L, which mapped us from the positives to the reals, satisfying two properties. L1 being the property that the derivative of the function was 1 over x, and L2 being the property that when you plug in 1 to this function, you get 0. So we proved that there exists a unique function satisfying these properties, and in particular, that function was the integral from 1 to x of 1 over t dt. And so since this function was unique, we gave it some notation, and we call this the log function. So this is what the log function is, and we demonstrated that it does have a derivative of 1 over x by the structure given here. So when we differentiate this integral using the fundamental theorem of calculus, we do end up with 1 over x. Now as for e to the x here, we haven't actually called this function by this name yet, but this is the exponential function actually, and so as we'll see in a moment. And so what we said was that there was a unique function e mapping the reals to the positives, which satisfied these two properties. E1, the property that e prime of x was itself, and E2 being that when you plug in 0 to this function, you get 1. And so the unique function which satisfied both of these properties was the inverse log function. And so we defined the exponential function, exp of x, was defined to be the log inverse function. Now this function, we saw amongst other things, it satisfied this property of the derivative being itself, and again we'll address why we're calling it e to the power x in just a moment, but going up to this top question here, how do we define real exponentiation? Well, we were able to do this in terms of the exponential function. We said that a number a to a real power x was by definition the exponential function of the exponent x times log of the base a. And so this was what it meant to do real exponentiation. And so finally coming to this question of why do we focus on e over other numbers regarding exponentiation, we saw one of the properties of the exponential function gave us the fact that the exponential of 1, if you raise that to the power x, using our definition of real exponentiation now, this worked out to be the exponential of x. And so in this sense, exp of 1 generated the entire exponential function. And so we gave exp of 1 some special notation. We called it e. So e was defined to be exp of 1, and this addresses this sub-question here as well. And so why we focused on e over other numbers regarding exponentiation is because it had this property of being able to generate the entire exponential function. So coming back now to the e to the power x function, we see that e to the x, what this is, by definition, e is exp of 1. And so this is exp of 1 to the power x, which we saw was exp of x. And so in this way, we see that these are the same function, and the function is generated by this number e and raised to this power x. And so this really is the exponential function, and it has the properties that we asserted. So now we've answered all our questions that we had at the beginning using this definition of the logarithm and the exponential function. So this really concludes this first video on real exponentiation. We've introduced the fundamental functions that we need, log and exp, and based everything off of them. And so far what we've done is we've addressed the structural properties of the log and exp functions. What's still left to do is talk about quantitative aspects. We really haven't been able to do any numerical computations regarding these functions yet. We just have structural properties right now. So that is going to be left for the next video. This one has certainly gone on long enough. We'll leave it to be continued for now. But if you have been, thank you very much for watching.